A vibration in a string is a wave. Usually a vibrating string produces a sound whose frequency in most cases is constant. Therefore, since frequency characterizes the pitch, the sound produced is a constant note. Vibrating strings are the basis of any string instrument like guitar, cello, or piano. Wave. The speed of propagation of a wave in a string is inversely proportional to the square root of the linear density. However, this derivation is only valid for vibrations of small amplitude. For those of large amplitude, is not a good approximation for the length of the string piece. The horizontal component of tension is not necessarily constant, and the horizontal tensions are not well approximated by frequency of the wave. Once the speed of propagation is known, the frequency of the sound produced by the string can be calculated. The speed of propagation of the wave is equal to the wavelength divided by the period, or multiplied by the frequency. If the length of the string is, the fundamental harmonic is the one produced by the vibration, whose nodes are the two ends of the string. So is half of the wavelength of the fundamental harmonic. Hence one obtains Mersenn's laws. Whereas the tension is the linear density, and is the length of the vibrating part of the string. Therefore, the shorter the string, the higher the frequency of the fundamental. The higher the tension, the higher the frequency of the fundamental. The lighter the string, the higher the frequency of the fundamental. Moreover, if we take the nth harmonic as having a wavelength given by, then we easily get an expression for the frequency of the nth harmonic. And for a string under a tension T with density, then observing string vibrations, one can see the waveforms on a vibrating string if the frequency is low enough and the vibrating string is held in front of a quartz screen such as one of a television or a computer. This effect is called the stroboscopic effect, and the rate at which the string seems to vibrate is the difference between the frequency of the string and the refresh rate of the screen. The same can happen with a fluorescent lamp, at a rate that is the difference between the frequency of the string and the frequency of the alternating current. In daylight and other non-oscillating light sources, this effect does not occur and the string appears still but thicker, and lighter or blurred, due to persistence of vision. A similar but more controllable effect can be obtained using a stroboscope. This device allows matching the frequency of the xenon flash lamp to the frequency of vibration of the string. In a dark room, this clearly shows the waveform. Otherwise, one can use bending or, perhaps more easily, by adjusting the machine heads, to obtain the same, or a multiple, of the AC frequency to achieve the same effect. For example, in the case of a guitar, the sixth string pressed to the third fret gives a G at 97.999 Hz. A slight adjustment can alter it to 100 Hz, exactly one octave above the alternating current frequency in Europe and most countries in Africa and Asia, 50 Hz. In most countries of the Americas, where the AC frequency is 60 Hz, altering a hash on the fifth string, first fret from 116.54 Hz to 120 Hz produces a similar effect.